6.3 with a very important theorem that will allow us from now on to represent any linear transformation as a matrix multiplication transformation. And in order to do that, theorem 610 says that all we need to do is look at what happens to the standard basis vectors. In Rn, they would be E1, E2 through En. In R3, we know these guys by I, J, K. So we put I, J, K, or the standard basis vectors through the linear transformation, and then the image of the standard basis vectors, we put them together as a matrix. We make them the columns of a matrix. And now we have the linear transformation matrix for that specific transformation. This matrix is called the standard matrix for the transformation. Let's see exactly how that works with numbers. Once you watch this video, you'll be ready to do problems 3, 5, 11, 17, and 33 in your homework. So this is problem 12 in your homework. If we were asked to find the standard matrix for the transformation that takes our three vectors, right? So vectors with three components into R2 in this way. So we say that our transformation T takes vectors from R3 and maps them into R2. So in order to figure out what this standard matrix for this is, we're going to have to take the standard basis vectors from R3. We know them by the name I hat, J hat, and K hat, and we put them through the linear transformation, and we see what we get. So the image of these vectors under the transformation will form our standard matrix A. So the first thing we do, we take I, 1, 0, 0, and put it through the transformation. That means x is 1, y is 0, and z is 0. So that gives me 2, 0. We take j, 0, 1, 0, put it through the transformation, and we end up with 1, 3. And then we take k and we put it through the transformation, and we end up with -1, 0, -1. So now we found that the standard matrix for our transformation, we're going to take the images of the standard basis vectors and turn them into columns. So 2, 0 becomes a column, 1, 3 becomes a column, 0, -1 becomes a column. So now instead of doing this with our input vectors, we can just multiply our input vectors by this matrix. For example, in order for me to find the image of V, I could put x0, y1, and z-1 through this formula. Or I can say, well, the transformation of 0, 1, -1 will be given by multiplication by this matrix. And so my image is going to be 2 times 0 plus 1 plus 0, and then 0 plus 3 plus 1, that's 4. So this two-dimensional vector is the image of 0, 1, -1. All right, so let's look at a matrix that's a little bit, like a transformation that's a little bit more complicated. Let's say we have to find the standard matrix for the projection onto the vector negative 1, 5. So what we're really looking for, so let's say you have all of R2 here. Hey, Buckley, come here. Buckley. And here's my vector negative 1, 5. I want to find a matrix that projects any vector in R2, this guy, onto my vector negative 1, 5. So any vector at all, it could be this projected onto the vector. If I have a vector going this way, its projection onto my vector negative 1, 5 will look something like that. So I'm projecting it onto this direction. Right, so projection onto my vector negative 1, 5. Negative 1, 5 is a fixed vector. It should stay in the formula. So what I'm going to do, just like I've done before, I'm going to put the standard basis vectors in R2 through the transformation and see what happens. So I want to look at the image of the vector I, which is 1, 0. So now my vector V, my changing vector is going to be 1, 0. I want to see this guy's projection onto W. My W is negative 1, 5. So the projection formula, this orthogonal projection formula, tells me to do the dot product of V times W. So I'm going to multiply 1, 0 with negative 1, 5. Divided by the magnitude of W squared. So that's negative 1, 5, the magnitude of that squared. And that is the scalar multiple of negative 1, 5, right? So I'm projecting onto negative 1, 5. So all of these projections here, they're going to go in the same direction. So they're going to be scalar multiples of negative 1, 5. So I'm going to multiply it by negative 1, 5. So let's see. Up here I have a scalar. Down here I have a scalar. This is negative 1 divided by the square root of 1 squared plus 5 squared, right? That's the magnitude of W squared, times negative 1, 5. So what happens to the image of 1, 0? Well, it gets sent to the vector negative 1 over 26 times negative 1, 5. Real quick, we're going to see what happens to the image of the vector 0, 1. So for that, I'm going to find the dot product of 0, 1 with negative 1, 5 divided by the same thing I divided before. So that's going to be 26, right? The magnitude of negative 1, 5 squared is 26. And then I have to multiply it again by negative 1, 5 because I am projecting this guy, J, onto negative 1, 5 again. So up top I get 5. So I have the scalar multiple in this direction is 5 over 26, and then multiply that by negative 1, 5. So now my standard matrix for this transformation will be given by these two guys made into a column. So that's going to be 1 over 26 and then negative 5 over 26. And then these guys made into a column, negative 5 over 26, and these two, 25 over 26. Now, to find the image of V, so now I am given a specific, I didn't bring it over. So let's try to find the image of a vector, let's say, I think number 32 had 2, -3 in there. So what we're going to do is to put this vector through the transformation. Instead of going through this computation again, we're just going to multiply it by this matrix. So we're going to say, now, you know, this, you see that there's a multiple of 1/26 everywhere. So you can make your life a little bit easier because, now let's just do this. 1/26, -5/26, -5/26, 25/26. We're going to multiply this by the vector 2, -3. And now we end up with another two-dimensional vector. So that's 2/26 plus 15/26. And then these guys hitting this, so it's -10/26 plus -75/26. So we end up, in fact, with 1/26 times 17, and this is going to be -85.